All right, this continues section 5.3. We're finding input values based upon a given output value. So first of all, we have to understand that f of x is the y value. That's the output value. So when we see f of x is equal to this, then what we're asking is to find the x value, the input value. So if the input value, the f of x value to the model, and then we can solve for the independent value given we have a model. And if we have a table, then we're going to look across the table at the f of x value, the dependent value, and we're going to look up to its corresponding independent value. And if we have it on a graph, we'll start at the y's, we'll go over to the graph, and then we'll follow it down to the independents. So we're going to look at our same exact three examples, except for now, instead of using the independent to get to the dependent, we're using the dependent to get to the independent. So part A here, we have f of x is equal to 9. So f of x, the value f of x, we're going to replace with 9, and that's equal to 2x plus 3. And as soon as you replace that left side, that f of x, with the value 9, you see, oh gosh, I just have a linear equation in one variable. And so I'll go ahead and solve it. I'll use my addition property first, and then once I have that, then I can use my multiplication property to multiply by the reciprocal and finish it up. And so now I know that x is equal to 3. And once I have that, then I can rewrite this, right, that f of 3 is equal to 9. And that says the whole story right there. Now our next one, we have the table. So in the table, I have f of x is equal to 9. The dependent is equal to 9. And so now I follow it up to the independent value, which is equal to 1. So f of 1 is equal to 9 is what I'm going to write down there, and that's my answer. And then part C, again, I'm going to go up the y's to 9. I'm going to come across to the graph, and then I'm going to come down here, and I get f of 1 is equal to 9 again. Now, it's just a happy coincidence there that B and C are exactly the same. There's nothing related to those, though. Remember, this one I had to go to the y-axis. I had to find the 9, come to the graph, and go down vertically to what the x was equal to. All right, now, function notation can also be used to solve equations. And when I solve the equations with this, then I'm saying the same thing as I was saying to solve equations before, right? So in other words, I can use this function notation to write the same thing as I would with slope-intercept form, right? F of x is equal to 2x plus 5 is exactly the same as saying y is equal to 2x plus 5. And so this is just another way with our function notation of writing the slope-intercept form. And as a result, when I see something like this, don't forget that I can still find values, right? I can let my x equal 0, and I'm still substituting this in like this, and that's meaning to find my y-intercept. And so what I found when I find f of 0, I found my y-intercept. X is equal to 0, y equals 5. If I want to find my x-intercept, I'm going to say f of x is equal to 0. And that means 0 is equal to 2x plus 5. And when I say that, then I'm solving for x. And so negative 5 is equal to 2x. And so x is equal to negative 5 halves, and that's finding my x-intercept, and it's using the function notation to do it. So this is how we would represent an x-intercept. And that pretty much brings this section full circle to the last two sections that we were dealing with, and showing how function notation can actually be used there as well.